Hello, my name is Emma Carraher, and I'm an undergraduate student at Purdue University studying computer science. And today, I want to talk about Dr. David Chaum's disavowal protocol. When you sign something with your digital signature, you need a way to prove that you didn't sign something if someone claims that you did. So this is a way to do that. Take Patty. Just a quick review. I'm going to assume you already are familiar with this. Your signature is X. When you sign something, you take m to the power of x, and you get a sigma. And knowing sigma and m, it is computationally infeasible to figure out what x is. So you have a public y and a g. Eve comes in and claims that you've signed some message m. If that's true, then sigma that she presents equals m to the power of x, which is your signature. If she's just making this up, if you didn't actually sign this, then those two would not be equal. In order to prove whether or not you did sign that message, we need a third party, Victor. Now, Victor knows these public variables that we've mentioned earlier, including y, sigma, which Eve claims to be your signed message, what the original message is, your g for your signature, and some k. This k needs to be not too large and not too small. Victor then computes two random variables. B is any random with no limitations, and A needs to be from 0 to K. Victor then computes U and W as shown, and sends them to Patty. Patty does not know A and B, but she does know U and W, so she needs a way to figure out what A is. If she can figure out what A is and send it back to Victor, then she can prove that she did not sign this message. We're going to first assume that everyone is going to be honest. So first, Patty takes the U and W and computes rho, such that U to the power of x over W is rho. This then simplifies to this once you substitute the public variables that are known, and as you see, y and g to the x are the same, so that cancels out, and you end up with rho equals m to the power of x divided by sigma to the power of a. She then computes a series of betas. There are going to be k number of betas. For each j between 0 and k, she computes the message to the power of her signature divided by sigma, all to the power of j. Now at some point, if a is actually in between 0 and k, like it's supposed to be, rho is going to equal beta when j equals a. So when they equal, she knows what j is, and thus knows what a is, and can send back a. And because she knows what a is, she can send that back to Victor, and therefore prove that she did not sign this message. If she did sign the message, and she was being honest about it, then m to the power of x and sigma over sigma, that would cancel out to be 1. And so rho would just be 1. Same thing for beta. All of the betas would be 1. Because rho simplifies to 1, and all of the betas simplify to 1, then there's not one particular j where that makes beta equal to rho. So she cannot find a, and thus cannot prove that she didn't sign it, because she did. So let's say that Patty wants to lie. Maybe she doesn't want to hold up her end of the bargain, and she wants to manipulate in some way. So let's say, for example, she's going to manipulate it by saying her signature is actually L. So instead of calculating rho to be u to the power of x over w, it's now u to the power of L, which then simplifies as such like we did earlier when we substitute the public variables. But you see, g to the power of x and g to the power of L are not the same anymore, so they don't cancel out. So you end up with this. The first part is what you wanted from earlier, but now you have the second part, that's g to the power of b times L minus x. She knows L and x, but she does not know b. And because of that, rho just turns out to be some garbage variable, so that she can't compute beta for any of the betas to actually equal rho. So she would just have to guess, and she'd have 1 over k chance of guessing correctly. That's why you want k to be fairly big, but you also want it to be small enough that it's reasonable to compute that many betas. So as a summary, if Patty lies, she cannot find a because rho and beta will never be equal. If Patty did sign the message and she was being honest, then the row would equal all of the betas, and therefore she cannot find what A is. She can only find what A is if she did not sign the message and Eve was lying.